Язык какой?
Ну, язык на ваше усмотрение. У нас обычно слайды всегда по-английски, а язык на усмотрение докладчика.
Нет, ну, если, как говорится, может, людей на английском языке не будет, может, нет смысла на английском как-то? Вот что я
Ну,
хотел сказать.
пока нет. Нет, тут, правда, есть Герхард Рахер.
Ну, может, тогда на английском будут тогда уже, да?
Ну, наверное, да.
Ага.
Мгм.
Все. Hello тогда.
Yeah, so today our speaker is Rinat Gumerov from Kazan Federal University, and his title is On Properties of Complex C-star Relations. Please.
Thank you very much. First of all, I would like to thank the organizers of the seminar for possibility to give a talk, and I would like to thank all participants for interest and for attention for this talk. I would like to say that it is based on the result of my joint work with Professor Ekaterina Lipacheva and my postgraduate students Bernikov, Igor, and Kirill Shishkin. The origin of our studying. Now, the talk is devoted to the universal sister algebras, more precisely to categories which determine the universal sister algebras. We are given a set of generators X and a collection of relation R for the elements of X and disjoint set X star. For each X from the set X, we consider an element X star. We
Yes,
have the following
Renat, I shall interrupt you with apologies because I mistook the time, because here in Athens there is another time. So great. Apologies and please continue. We are with great interest we listen to you. Bye. Please.
So the problem is the following. To define a universal algebra generated by a set of X subject to relation R. In the following sense, we must have the following universal property. For every sister algebra A, having elements AX indexed by the set X satisfying the relation R, there exists a unique star homomorphism from the universal algebra to A such that X is mapped to AX for each element X. Here we have the following questions. What is a relations? What conditions should a set of relations satisfy in order to define a universal sister algebra? As usual, we have the following easy examples of sister algebras, and everyone understands what is a sister algebra generated by relations. For example, the matrix sister algebra, the full matrix algebra, is a universal sister algebra generated by the set of matrix units which are subject to the relations written here. The algebra of complex operators on separable Hilbert space is a universal sister algebra generated by the countable set of generators subject to the same relations. The famous Toeplitz algebra generated by one isometry also is universal sister algebra, and by Coburn's theorem, the Toeplitz algebra is isomorphic to the sister algebra of all bounded operators generated by the right shift, where En is the standard basis here written, and here definition of shift. For example, algebra of continuous functions on the unit circle is the universal sister algebra generated by one unitary operator. And for example, there is no universal sister algebra generated by one element set subject to the relation. Here is the normality condition. And what should be first? Should I say here that in the definition of the notion of relation, there has been much discussion, as one can find in standard references in the books by algebra, in pure algebra. One considers in algebraic context where we have free objects. For example, if we consider a group or ring, a relation is simply an element of a free object. And without free object, how does one should define what is a relation? Also here I should say that all authors agree that involutive polynomials, which are easily forced via quotient method as in the algebraic case, should be considered as relations. Most authors also include known bounds as relations. For example, in the fifth example, if we consider the bound relation, we consider the inequality that the norm of x is less than 1, then we have a universal sister algebra. Also, analytic functional calculus agreeable with involutive homomorphisms. For example, one can consider order relations to define a universal sister algebras. And here, several words about history. Coburn in 1967 considered the triplet algebra, which was mentioned above. Kunst considers the sister algebra, which is generated by an orthogonal projection with mutually orthogonal ranges. The famous sister algebra of irrational rotation was introduced by Riffel. And in 1985, Blackadar gave a systematic treatment of universal sister algebras on sets and generators. He considered the relations of the following form, where P is a polynomial in non-commutative variables with complex coefficients. Indeed, the first example of Blackadar was any sister algebra. Any sister algebra, he says that any sister algebra is a universal sister algebra with respect to all its elements and all star algebraic relations in this algebra. However, this is not very helpful definition to define a universal sister algebra in this way. One usually wants to choose a smaller list of generators as well as a smaller list of relations and hope that this small list of generators and relations encodes all other relations of this sister algebras. In 1988, Phillips studied the pro-sister algebras, and his paper, he suggested some axioms which were used by, excuse me.
Hello.
Извините, у меня доклад. Олег.
А меня, извините, у меня почему-то не включается видео. Ну, хотя бы звук есть.
А вы появлялись, Александр Яковлевич?
Да, после чего пропало. Ну вот, ну будем надеяться, что это время. Потому что я слушаю с большим интересом. Пожалуйста, давайте.
Loring suggested a categorical approach to relations that correspond to universal sister algebras. In the framework of this approach, one deals with the categories that are called the sister relations, and the talk is devoted to these categories. Here, first I recall the standard construction of a universal sister algebraic subject to relation. This construction is contained in Blackadar paper and in others. Let's consider the involutive algebra of non-commutative polynomials. Take any subset R in this algebra and consider two-sided involutive ideal generated by this subset. Then consider the quotient. It is universal involutive algebra generated by X subject to R. For each C from the quotient, we put by definition what is a semi-norm of C. If this value is finite for all elements of the quotient involutive algebra, then this value is sister semi-norm. In this case, one takes the null subspace and complete it. The universal sister algebra is obtained as required. And I recall that this algebra has the following universal property. For any sister algebra A with elements AX indexed by elements of X satisfying the relation R, there exists a unique star homomorphism from this universal sister algebra to A, such that X is sent to AX. Now we will speak about Loring approach. For a given set X, he suggests to consider the null sister relation on X. It is category whose objects are all functions of the form where A is a sister algebra. For two objects, for two arrows, a morphism from J to K is any star homomorphism of sister algebra, making the following triangle diagram commute. And he supposed to take as definition the following axiom. These axioms are very close to axioms which were supposed by Phillips in the work of 1988. A sister relation on X is a full subcategory R of F X satisfying the following axioms. The function from X to 0 sister algebra is an object of this category. Then if we have an injective star homomorphism of system algebras and any function from X to the domain of phi, the composition of phi with F is an object of R. Then F is an object of R. The third axiom is the following. If phi is a star homomorphism of system algebras and F is an object of R, then the composition of phi and F is an object of R. For me, it is easier to remember this axiom. I consider relation only as polynomials, and here some conditions which are satisfied for polynomial relations. Now, the fourth axiom with index F, if we have a finite number of objects, then the function, we say product of this function, is an object of R. Loring suggests to call objects of this relation as representations. And now, the main definition of our compact system relation. Take any family of system algebras, consider the direct product. A system relation R on a set X is said to be compact if in addition the following condition is satisfied. It is almost the same as C4F axiom. Here we only take the product of an arbitrary family of elements of category R. Cardinality number of the set lambda is arbitrary. And Loring proved the following theorem. Here some reformulation of result from the paper by Loring. Paper number 2, it is paper of Phillips and no, yes. And here also there is paper of Hedwig, Kaonga and Mathis in Korean Mathematical Journal. Loring also used their paper. And we have the following theorem. Let R be a sister relation on a set X. Then R is compact if and only if there exists an initial object in R. And this initial object is called a universal system algebra.
Good.
For a compact system, here I give definition. For a compact system relation R on a set X, we take an initial object. The system algebra A is denoted by C star R and is called the universal system algebra. So that by the definition of an initial object in an arbitrary category, we have the following property. For every representation J of R, it is object of this category. There exists a unique star homomorphism of system algebras K from universal system algebra to B, such that the following diagram is commutative. In what follows, we denote the star homomorphism K by J with bar. It is easy to see that we have the following relation for these homomorphisms. We use this relation in the following construction of the functor. Now, we have the following purposes. To show that every compact system relation is isomorphic to a polynomial relation, I will give now the definition of polynomial relation. Informally speaking, we would like to show that every universal system algebra is defined by a collection of star polynomials. And another purpose is to obtain a categorical criterion for the existence of universal sister algebras. As it was said, the talk is based on the result of our joint work with Professor Lipacheva Ekaterina Vladimirovna and with my postgraduate students Igor Sergeyevich Bernikov and Kirill Andreevich Shishkin. Yes. Now we construct a functor between compact sister relations. So we are given two compact sister relations, R1 and R2, on sets X1 and X2 respectively. Let us consider the initial objects, I1 and I2. Suppose that we are given a star homomorphism of sister algebras, alpha. So it is a homomorphism between universal sister algebras. And now we will construct a functor which is associated with alpha. Firstly, take an object of the category R2, J. Consider a homomorphism, J with bar, whose domain is the universal sister algebra of the second category, and consider the following composition, J bar, alpha, and I1. By one of the axiom of sister relation, namely the axiom C3, we have that this composition is an object of the category R1. By definition, we put that the functor F alpha, which we are constructing, stands J to this composition, the formula number 1. And now I should construct an arrow function. We take any morphism in the category R2 such that the following diagram is commutative, and consider two objects, F alpha J and F alpha K, and consider the diagram. It is easy to check that the star homomorphism makes this diagram commutative. So it is correct to put that the value of the functor at phi is phi itself, the formula number 2. It is easy to check that F alpha preserves the identity morphism and the composition of morphisms. So the formulas 1 and 2 above define the functor F alpha, contravariant functor, as desired. And we have the following theorem. Let we have two categories compact, R1 and R2, on sets X1 and X2 respectively. Let we have the initial objects, then every homomorphism of universal sister algebras of these categories generates the functor F alpha. Moreover, if alpha is an isomorphism of these sister algebras, then this functor is an isomorphism of categories. And in the sequel, we shall use this isomorphism. Now, I would like to give a definition of involutive polynomial relations. First, I will give a definition of polynomial pair. We are given a non-empty set X, and we consider the involutive algebra of all polynomials in non-commuting variables X and X star. For a non-empty subset P of algebra of all polynomials, the pair XP is said to be involutive polynomial pair, because we have a free star algebra for every mapping F from X to an involutive algebra. There exists a unique star homomorphism F tilde, which is an extension of F to the whole free star algebra F of X. Definition: a function F from X to a sister algebra A is called a representation of involutive polynomial pair XP, provided that P is contained in the kernel of F tilde. I recall that F tilde is an extension of mapping F from X to A. Further, we are given a polynomial pair XP, and now we construct a category. Objects of this category are all representations of this polynomial pair, and a morphism from J to K is any star homomorphism of sister algebras A and B, such that the following diagram is commutative. Thus, this category is a full subcategory of the null sister relation F of X, which was defined at the beginning of our talk. Now, the following important definition for our talk. The category RXP is called a star polynomial relation associated with a star polynomial pair XP. We have the following proposition. For any polynomial pair XP, the polynomial relation RXP is a sister relation in the sense of Loring. So now we turn to our example 5. Why the relation, the normality relation X star is equal to X star X does not define a universal sister algebra. I recall that we have one point set X, and we consider the following polynomial. Consider the polynomial relation associated with this polynomial pair, and let's consider any non-zero sister algebra A and take any non-zero normal element in this sister algebra. For each natural number n, we consider the following function f indexed by n. It is easy to see that it is really is an element of category R. It means that the extension of Fn, I recall that it is Fn with tilde. Its kernel contains this polynomial. It is easy to see. Obviously, we have the following relation for the norms. And by axiom C4, and we see that axiom C4 is not valid in this category. So this category is not a compact sister relation, and so we don't have a universal sister algebra. We don't have an initial object in this category. Now we give the following definition. If a star polynomial relation R has an initial object I, then the sister algebra A is called the universal sister algebra generated by the star polynomial pair XP and is denoted by sister XP. We have the following proposition, theorem 2. For every sister algebra A, there exists a star polynomial pair XP such that this sister algebra is a universal sister algebra generated by the polynomial pair XP. To prove this proposition, it's enough to consider the star polynomial pair consisted from A as set X and as set of polynomials, involutive polynomials. We take a kernel of the extension of identity mapping and prove that identity mapping is an initial object in the star polynomial relation R A kernel tilde 1A. And we have the following corollary. For every sister algebra A, the star polynomial relation R A kernel 1 tilde A is a compact sister relation. Now we go to the next slide. Using functor, which was constructed in the theorem 1, and using the previous result, we prove the following theorem. Every compact sister relation is isomorphic to a star polynomial relation. So, indeed, every relation which was defined by loading, which has an initial object, it is generated by a polynomial pair. Now, we are going to speak about another. Now we start the second part of our talk. I recall that the aim of this part is to obtain a categorical criterion for the existence of universal sister algebras. I hope briefly recall some standard definitions from the category theory. So, let we are given a category C, and we consider a small category I. I recall that the family of objects of this category constitute a set, and for any two objects, the family of morphism between two objects is also a set. A functor D from this small category to the category C is called a diagram in C of shape I. A cone on the diagram D is a pair V tau, where V is a constant functor and tau is a natural transformation from V to D. Or in other words, we have an object V in the category C, and we have a family of morphisms, tau I, tau G, here indexed by objects of category of the small category I, and such the following diagram is commutative for every morphism in the small category I. And such a cone of the diagram is called a universal cone if for every cone V prime tau prime on D there exists a unique morphism phi such that the following diagram is commutative. A universal cone on the diagram D is usually called a limit of the diagram D. And any category is said to be complete if it has a limit for every diagram in this category. And the following classical result is the following. From the book by MacLean, a category is complete if and only if it has all products and equalizers. I recall now what are products and equalizers. Let lambda be a set. We denote by L the discrete category. This is category whose objects are elements of sets, of any set, here set lambda, and all morphisms are the identities. Let C lambda be a family of objects, and consider the diagram D from L to C, which send an object lambda to the object C lambda in C. A limit of this diagram is called the product of the family C lambda. It is denoted by the following way. Morphisms P lambda are called projections. And I recall the universal property. Also, as usual, this property is given as definition of product. For every object C in the category C and every lambda indexed family of morphisms F lambda in C, there exists a unique morphism F such that the following diagram is commutative. Now I recall the definition. Now I will formulate the following lemma. One says that a category has all products if every family of its objects indexed by any set has a product in this category. Lemma 1, every compact sister relation has all products. Now, equalizers. Let E be a category with two objects, A and B, and with two morphisms, U and V, and with no other morphisms except for identities. Let we have two morphisms of this category, or no, of the category C, another category, with the same domain and codomain. As usual, one refers to such pairs of morphisms as parallel morphisms. Consider the diagram D in C of shape E such that D sends U to V and V to G. A limit of this diagram D is called an equalizer of F and G. And we have the following universal property of equalizers, which is usually also can be considered as a definition of equalizer. So, equalizer of two parallel morphisms is a pair where E capital and small e, where the capital E is an object of the category C, and E is a morphism of C such that the following two compositions are the same, and the following universal property holds. For every morphism H from some object H, such that the following relation holds, every such morphism can be factorized uniquely through E. This means that there exists a unique morphism D from H to E, such the triangle on the left-hand side of this diagram is commutative. And in the case, if each pair of parallel morphism in a category has an equalizer,
excuse me, Renat,
say that C has all equalizers.
Excuse me, in abelian categories, it is kernel or what?
In what is? Excuse me?
If our category is abelian, these equalizers are kernels, or I'm wrong?
Kernel, I think, kernel.
It seems that the equalizer is the kernel of f minus g, of the difference between
f. Yes, of f minus g.
Yeah, so it is reasonable generalization, yes, of this. Okay, please continue.
Okay, we have the following lemma. Every compact cyst relation has all equalizers. In the proof of the above two lemmas, we explore categorical constructions in the category of cyst algebras, and these are homomorphisms from the papers by, I don't remember exactly how to say, number 9, the reference, Hoshkam Tavakoli, in the Journal of Australian Mathematical Society, 22. Maybe Alexander Yakovlevich knows these persons.
No.
No?
I just think as our names are sound from somebody. English person, for example. Okay.
Using lemma 1 and lemma 2 and standard theorem, standard theorem, I mean that any limit can be constructed from two basic limits, namely product and equalizer. We have the following result. Every compact sister relation is a complete category. Now, our final result, it is an application of the previous theorem. We have the following criterion for the existence of universal sister algebras. Namely, we have the following theorem. Let R be a sister relation, then the universal sister algebra of this category exists if and only if this category is complete.
Okay.
That's all. Here references. Thank you very much for attention.
Yes. And we thank you for a very interesting talk and, in my opinion, very actual topic of it. So what are questions? Anar, of course, has...
Thanks, thanks for talking. It's so interesting. I have a question concerning your theorem. Like you said that whatever sister algebra you have is actually a universal one for some set X and relations. Well, what can happen if your sister algebra is generated by just single normal element? Is it possible to find that set X and relations?
Only one normal element?
Yeah, you just take a normal operator in Hilbert space and get the C-star algebra generated by single element. And then you said that it will be a universal C-star algebra, is it? So then there is that set X and relations. Is it possible to find out what is that?
So we take an arbitrary normal operator and generate C-star subalgebra, you mean?
Yes, that's right.
And
so it's a universal by your theorem.
What is X and what is a relation?
Yes, that's true. Is it possible to find out? Because it should be something interesting, right?
I think that I'm not sure that I can find it.
I see. Okay.
I think that first of all we take this polynomial, then we should take a norm of this normal element, consider a bound for this norm, which is equal to its norm, but
yeah, probably it should be
whether we obtain any universal algebra or no, I am not sure.
I see. Anyway, it should be big set, right? So not just the same relation. It should be something bigger set, bigger relations.
Yes, I also think so. And I only can say that now we try to find some relation in terms of spectrum of elements.
Okay.
Maybe, but
okay.
It is not easy to find in any case some concrete set of relations. We have some result, but usually there are a huge list of relations when you try even for easy algebra, for some unknown algebras, usual algebras.
Okay. I see. Well, I have one more question concerning theorem 1. Concerning compactness. Is it only for existence of initial objects, or you are using the proper definition in the proof? But you know, the compactness definition is a bit different, right? So the mapping to a product. So in theorem 1, you said.
In theorem 1, it is theorem 1 where functor is constructed.
No, the presence of universal. Yeah, probably this one. Yes, probably this one. So always you're saying compactness. Is it only for presence of initial objects? Am I right?
Yes, only we use the presence of initial objects.
Okay, yes. But definition itself is a bit different, right? It's a bit complicated. I mean, just presence of a map from the product to product. Yeah, okay, I got it. So you're only using the presence of initial objects. That will be enough for you.
Only initial objects. It's enough.
Okay, yes, thanks.
Okay. Other questions? Okay.
Well, I have a question
yes.
about possible generalizations. So at the very beginning of your talk, you mentioned a paper by Chris Phillips about relations in pro-C-star algebras. Is it possible to extend your results, or maybe some of your results, to relations in pro-C-star algebras?
We have not thought about it.
For example, theorem 5 on characterizing relations which are which have a universal object in the category of pro-C-star algebras. It seems that a condition on R should be more flexible, because it's in general it's possible to there are some relations which don't have a universal C-star algebra, but which admit a universal pro-C-star algebra. So that would be interesting to think about it.
Suggestion. Yes, thank you. Yes.
Okay. So in this case, let us again thank Rinat Nelsonovich, yes, for his very interesting talk. And the next Friday will be the end of this semester. Yes. And we shall have a talk of a young, talented mathematician. Bilic is his name. Yes, sir?
Yeah, Boris Bilic.
Boris Bilic. And where is he now? In higher school of economy?
No, he is in Göttingen and at the same in Haifa.
Yes. So and what is well, okay, we shall discuss. Again, I apologize for that unfortunately times in different countries are not the same. Yes, but and sometimes it happens. Even with speaker, you remember how Yulia thought. Yes, no, so well, next time I shall try to be more attentive. So thanks for all, and we shall meet the next Friday, I think, to common pleasure. So bye-bye.
Thank you very much, Renat.
Thank you for attention for you.
Have a nice weekend. Bye-bye.
Yeah.
Bye-bye.
Bye.
Bye.
Bye-bye.
Goodbye.